Good morning, everyone. And I see familiar names. Thank you for joining us. And it's really my pleasure to host this seminar by Dr. Tong Yang, who is a postdoctoral fellow at McGill University. And his postdoc research is funded by the Swiss National Science Foundation. He completed his PhD in 2022 from Swiss Federal Institute of Technology, Zurich, and his research is focused on the formation and release of micro and nanoplastics, which is also our research interest in my lab. And he serves as a young editor for a very good journal, emerging but very impactful journal already, Environment and Health. And he's also a guest editor for a special issue on micro and nanoplastics, and he's a reviewer for journals including Environmental Science and Technology and Water Research. Both are the top-notch journals in the environmental field. So his work has been cited by UNEP and WHO, as well as EU reports. So there's no doubt Dr. Yang is a rising researcher in the field of environmental studies, especially emerging pollutants. So it's really our pleasure to host his seminar today. Please, Dr. Yang, the floor is the screen is yours. Please share your screen and start your seminar. Thank you.
Yeah. So I hope I'm doing all good with the right screen. So thank you, Jinkai, for inviting me to talk at this chair series seminar. I'm very honored to be the first one here. For those who don't know me very well, my name is Tong, and I'm now a postdoc at McGill Jingsha Liu's lab. And before I started working on PFAS this year, I'm an environmental chemist and modeler by training, and I have 6 years of experience on micro and nanoplastics. Half of my work was on the characterization side, which is the exposure of micro nanoplastics released from synthetic textiles. And the other half, which I'm going to share with you today, is the modeling part, which I modeled the environmental risk of those pollutants, emerging pollutants. And so to start with, the first synthetic plastic products is actually the celluloid. It was meant to developed to replace the evergreen billets. It was created with a good intention to save the elephants, but the texture wasn't just a perfect match. And nowadays, the plastic products have diversified, and we benefit a lot from those products that are more functional, cheaper, and they become actually inevitable in our daily life. So you can see the 6 common types of plastics starting with PET and then with SES, EPS. And the definition of plastic actually consists of 2 pillars. First one is the polymer, whether it's synthetic or natural. The second element is additives, which added to the different functionalities and the functionalities of the plastics. And there are 2 major categories in terms of production process. One is the overall property. One is the thermoplastics, and the other is the thermoset plastics, which once they are molded into their shape, it's hard to change it. And while we are enjoying the convenience of those plastic products, the chemical essence of them make them hard to recycled. We saw only 9% of them are recycled, and no doubt the others go to the waste. Last year, we conducted a material flow analysis of different plastics, 6 major plastics in China, before and after the plastic ban in Chinese policy. And we we kind of demonstrated the applications of different plastics in China versus in Europe. You can see in Europe, the majority of application sits here in packaging, and for China is the textile and packaging as well. And this material flow analysis actually not only look at from the production phase, but also till the end of life of the plastics. And no surprise, the large majority of the plastics end up in either incineration or landfill. And also, some of those important part of this waste also flows into the water environment, for example, and it does degrade, although very slowly, into small plastic debris, which are defined in this science paper, well-known science paper, as microplastics for those who are smaller than 5 milliliters. And for nanoplastics, ranges from 1 to 1,000 nanometers. It's worth mentioning that right now, this week features the INC4 meeting at Ottawa, and I'm also looking forward to see what is coming out of the negotiation. But before that, well, we need to realize those plastics are actually spotted like everywhere in global surface water and sediments. So this study actually mapped the concentrations of microplastics in surface water and the sediments. Once they persist in our environment, they can also interact with animals, such as like impeding the activities of large animals, and also can be very small microplastic can be ingested by small invertebrate. Another topic of today is the also very hot topic here in North America is the PFAS. As an example, so I demonstrated the structure of a legacy PFAS, which is PFOA, and it consists of a hydrophobic tail plus a hydrophilic and a hydrophilic carbonyl group. And this unique structure makes it both very stable, which because of the strong CF carbon chemical bond, as well as it's at the same time very mobile in the environment. So the PFAS, due to its unique properties, was widely applied in different products in our daily life, including the well-known the Teflon cookware, which is coated with a polymeric PFAS, and then also a bunch of different applications, including a very well-known aqueous aqueous foam, and that's usually used in firefighting trainings, and then it flows into the environment and stays there. And so those PFAS containing carbonyl group, the PFCS, is only a small branch of the thousands of PFAS chemicals, and they are also, as you might think of, they will be persistent in the environment, and due to their mobile characteristics, they are everywhere. So this is a very recent study, shows the mapping the concentrations of PFAS in the global surface water, and I believe, although there are some parts that are not measured, I believe it exists every corner on the planet. And some of the sampling spots, the sum of concentration of 20 regulated PFAS exceeded the local legislation, and as those red spots indicates. And recently, I also watched this very well-known movie, The Dark Waters, and it is about a lawyer, so this guy, Robert, who at the beginning defend for the big chemical companies as corporate lawyer, and then they found one case come into his vision while in his hometown, West Virginia. So a local farmer, Taft, his family, his farm, his animals are hugely impacted by unknown like circumstances, and then which was find out to be the a mysterious chemical called C8, which is we now know is PFOA, that sees a large the death of his animal and also the disease of his family members, so that the Robert has decided to defend for the health and for the local people. And one difficult thing in this whole case, which is still going on right now, is how to set a safety threshold for the regulators to regulate the local waters. And experimental results conducted in DuPont they insist they says that okay, PFOA in waters are at safe concentrations, but how to derive and decide this concentration for freshwater species or even for drinking waters is difficult. And here comes our research. Is also one of our research objectives to characterize the risk of emerging pollutants or in the environment. Usually when we talk about a risk characterization, we have to know, we have to get two-side information. One is from the exposure side, which is the monitoring data, either it's predicted or measured in the concentrations of certain pollutant. And the other side is the hazard information, like how toxic are they? And usually the ecotoxicologists use animal testing to decide the effects by conducting different experiments. There are two major effects. One is lethal effects corresponding to mortality. And then the second is usually for the most of environmental pollutants, they only cause sublethal effects, which means a long-term growth effect, reproductive effect, and even some only can observe like cellular level, the effects at cellular level. And for those of you who have done such kind of experiment, this curve, the dose response curve might not be alien to you, but I would like to just kind of like take 2 more minutes to explain a little bit for those who really don't understand it, because this includes a lot of crucial concepts in our study. And the lethal dose or lethal concentration is usually expressed as LD or LC, while the effect, which we refer, which includes the lethal effect, is EC expressed in EC. And seen from this graph, we can see those different data points are the solid observation data we conducted from, we obtained from the ecotoxicological experiment. And the y-axis is the x-axis is increasing dose we applied to those animals, and the y-axis is the percentage of organisms or percentage of at the population level, how many species were affected, showing an effect. And the EC50 you might heard a lot, which is we feed all this data into a curve, and then with the 50%, half of the population gets affected, the corresponding concentration is expressed as EC50s. And the lowest observed effect concentration is when you see an effect that is significantly different from the control group, and that's the lowest point in your set of concentrations. And the no observed effect concentration is when you have also a test concentration which is lower than the LOAC and is not significantly from the control. So what is important here is we take a second to digest this. So the NOAC, no observed concentration, is actually the precautionary concentration, most precautionary concentration in the all settings. And with that, so this whole modeling approach is based on the well-known species sensitivity distribution, which word by word, the sensitivity is the toxicity, and the species is because different species have different sensitivity to a pollutant, and we put them together, and sort them in a ascending way. X-axis we see the concentration, the NOAC, for example, ascending, while the more and more species gets affected, and this is the SSD. And we use this SSD, so the experts use this SSD to obtain a safety threshold in ECHA, so the European Chemical Regulation Framework. We use the PNAC at 5 percentile, and the corresponding concentration as the safety threshold derived from this SSD method. And what we do in our studies, we don't do the ecological test of cells, but rather we collect data from different peer-reviewed studies, and we know there will be different endpoints reported in different studies, but we look at the effect on population levels, such as growth, reproduction, And for plants, it's the photosynthesis, the very epic endpoints. And we set a system boundary, which is freshwater, for example, and then we normalize all the data to chronic NOAC, and then build based on the chronic NOAC into a SSD. And so these two assessment factor was used to normalize our data. First one is the dose descriptor. As we see various dose descriptor reported in different studies, we have to normalize them to be in order to be comparable. And you might recall that dose response curve, that we normalize everything into NOAC, and usually these previous studies show the different endpoints has the ratio to convert it to NOAC. It's like this. And then for we want chronic data more, and then if only acute toxicity is reported, then we try to convert them into chronic data using the assessment factor time. And it's so for different species or different they have different like time, which is suggested by the OECD test method to facilitate this conversion. And now comes maybe a little bit harder part, which is how we build this SSD with a probabilistic method. So this P stands for probabilistic. And usually we have only one, like when we have one observation. So we use this. How can we use this to predict the true value behind it? So observation versus true value, true toxicity is, of course, we believe the measurement concentration has the highest probability, while we also attribute a interlaboratory variability of the data. So basically, this is a probability density function. And we believe the true toxicity lies behind this distribution. And when it is more close to, the concentration is more close to the observation point, the more likely they are to be the true toxicity. And we also probabilistics the uncertainty factors, and by the measurement data divided by two assessment factors, we get a NOAC, a chronic NOAC, as a normalized distribution, which the mode value is the only one observation divided by two uncertainty factor here. And usually, and for those species which have more than one data point, we build this trapezoidal function, which we equally believe the concentration between the lowest one and the highest and the higher one, so that the probability between them are equal. And then two sides, we still use this triangular distribution. And for the for the species which has a lot of measurements data, we tend to equally believe them. Well, here is a little bit like, well, this wasn't up to date enough. So in between, there's still like stepwise distribution. So probability between them are equal. And now, once we have those probability functions for each different species, 1, 2, 3 to n, and here's how we construct the PSSD. So we use Monte Carlo simulation with the random sampling technique, and then we randomly sample in the distribution each point, which represents the true toxicity in the species, and then I put them into a SSD. So this is SSD1. I run once, and then I run it another time, repeat this process. Now I get another distributed SSD. So we repeat them for 1,000 times. So we get a cluster, a bunch of 1,000 SSDs. So you will later see it. But before that, I kind of may have additional information on this database. So we basically this study was conducted in 2019 and published in 2019. So the database only consists, back then, the microplastic ecotoxicity study in freshwater, only 53 endpoints, 14 species, and with 42 being chronic values. And in those different species, and we also included in our database the different shape information and polymer type information in the database. So now this PSSD with 1,000 simulations look like this. So this is the mean SSD distribution with the like the shaded area or the range of those distributions. So we kindly present in the PSSD the various information here. You can see the different polymer type, different colors, different shapes of different data points. And with that, we can actually extract this at fixed percentile, which is also a distribution of predicted no effect concentration. So this concentration is used as the safety threshold for the microplastic in the freshwater system. And in this study, we also collected the monitoring data. So the monitoring data was collected in different continents, and using the same method, we probabilisticized all those data, and then get this probabilistic distribution of environmental concentrations for different part of the world. And as you may record, the risk is all about comparing exposure versus its hazard. So by dividing these two values, we get a risk characterization ratio, which represents the risk of microplastics in different part of the world in freshwater system. And as we can see, worldwide, there is actually, so when it's close, when it is close to 1, meaning there is a chance like close to where the safety the environmental concentration is above safety threshold, there is a chance for the risk events to happen. So basically, except for Asia, well, some places, the most part of the world back then, back in 2019, was data was not like really risky in freshwater system. And we also update the hazard data last year. So we published this study in GHN, and we kind of updated the PNAC, and we found an interesting subtopic with the weather microplastics we built with limited data. We have to admit the data was not a lot, but with the limited data using the probabilistic approach, we can say that the weather microplastics are less toxic than the pristine ones. This probably be due to like the weather toxics, the weather microplastic may have their additives that already leached out into the environment, so then it's less toxic than the pristine ones. And of course, we need more study to confirm that. And microplastic size was influenced. So the different factors, the size is more influence more the toxicity than shape and polymer type. And we also observe the large variability in effect data as we include all of the study that meet the criteria, meet our inclusion criteria. So there's a lot of variability in effect data, even in one single species. And following the microplastic studies, I applied this approach during my PhD to assess the hazard of nanoplastics. So we also build this kind of PSSD. Again, the different colors represent different polymer type, and then different. So here the shape is actually another dimension, which I carefully examined the test material data to see whether or not the sodium azide, a biocide added to prohibit inhibit the microbial activity in the nanoplastics suspension. So whether or not it's removed or considered. And then we found that in this PSSD, the polystyrene nanoplastics are overrepresented, largely due to the availability of this kind of test material. And the additives, sodium azide, biases the toxicity. So if we take out those kind of studies, take out this kind of study, the PNAC actually increases a lot, which means at a higher concentration, the species will be affected. And that means the additives actually like lead to the overestimation of their toxicity, nanoplastic toxicity. And polystyrene nanoplastics in different subsets, they are higher than the other polymer type tested. But we have to admit that back then there wasn't many polymer type were tested there. And again, we track this PNAC for the toxicity comparison. And if we look at the microplastic and nanoplastic PNAC or its toxicity, so here, smaller the PNAC is, the more toxic they are. And here, so basically, micro nanoplastics actually they have larger PNAC without these additives, and also they are the toxicity is smaller than most engineered nanomaterials, and nanoplastics smaller than microplastics. And we only have the information available for conducting hazard assessment, while obtaining risk information, we still need more exposure data, which are like today very limited number of the monitoring data of nanoplastic in the environment due to the analytical gap. So now in McGill, actually applied what I've learned, and also to assess the hazard of PFAS in using the existing data. So the most recent similar study was kind of done 5 or 6 years ago, with more and more people doing those ecotoxicity study for PFAS. So we feel a need to update the information, and this time we not only look at the available study, but now we use a semi-quantitative approach to first evaluate the data, and then build different quality data sets to see the difference. And we include so this is the profile of a PFAS data, ecotoxicity data set in freshwater, and we look at the PFAS type, the carbon chain length, how many carbons are there, and then test endpoints, and then those descriptors. So similar approach, but this time what's different is we applied a scoring scheme that looks at the test method, whether or not they have met the test method, test materials, for example, whether they assess the test substance purity, and for the test organism, whether they measured the PFAS residuals in the organism. So one important criteria, which I want to highlight here, is the criteria 8. So basically, it is the most, well, it's a very important criteria, but even for the highest then high quality data, so this criteria seems to only be 30% to meet, or 40% here. Well, here 40%. And then if we look at the data sets, well, we built the PSSD for different sub-data set with different qualities, and we find this PNAC actually changes starting from the lowest quality paper or suboptimal quality paper, and then we see it first increases and then significantly decrease, and after that it kind of stabilized here. While we will see quality scoring larger than 7, larger or equal than 7. Now we somehow can trust those data better. And the lowest, using low quality data, underestimate the PFAS toxicity, as we see more larger PNACs. And this is a database we built above 7 points in freshwater. You have a lot of data here, and in PFCAS or PFSAS, which is the sulfonic group. And we have also legacy data, legacy PFAS data that was highlighted here. And the emerging PFAS, well, not a lot of them, but still quite okay-ish amount. And then if we look at the different effects by, for example, functional groups or from the carbon chain length, we found that for the carbon chain length in PFCAS, definitely we see they are different. So they are not, they don't exhibit the same level of toxicity. And with short chain PFAS, say, equals to 4, and they are higher PNAC, meaning less toxic. And generally, PFSAS also are more toxic than PFCAS, and the carbon chain length is significantly less toxic than the others. To kind of to more critically assess the effect of carbon chain length, we use the data from the same species. So we extract them using the case of PFAS as a lot of data were available, and this is the number of data points, number of species available in this PFAS with different carbon chain lengths. So those 5 are if the X5 don't have enough data, so we didn't show it here. And then we found the toxicity data in the same species, like you can see here. For 2 species, we have enough data to do statistical tests. And we found this difference is significant, which means carbon chain length plays an important role, although it's not that linear. But it is an influencing factor for PFAS toxicity. And for the same in the same study, some studies also conducted using different carbon chain length, which you can see like the general trend is like this. So some of the studies are also like high quality studies. Well, just to have like an overall comparison of the different ecotoxicity of different emergent or legacy pollutants, we found that PFAS studies highlighted in the boxes from our present study is actually they are somehow, well, those PFOA, PFOS are similar to the nanoplastics toxicity level, and while they are much less toxic than the like other pulps such as PAH. So now some like kind of like a wrap up of our studies. So basically we use a meta-analysis approach, statistical approach, to quantitatively summarize or derive a safety threshold for both micro nanoplastic and PFAS in freshwater system, and the data treatment, we use data treatment to facilitate the comparison, make sure they are comparable, and with that we can present a state-of-the-art understanding of the ecotoxicity using this quantitative approach. And then for the hard assessment, we found that data quality is actually crucial in this kind of assessment. And the statistical tests we've done to find the influencing factor are quite effective. We actually identify some influencing factors in their toxicity. And for the future, like how can we improve such studies? We definitely need to consider like data evaluation, not just take whatever is available there, but also before using them, we really have to come up with a way to critically assess what kind of data we're gonna apply. We're gonna can lead to a more reliable result. And for like the outlook of the micro nanoplast studies, so there is actually, so what I talked about the gap in analytical method, and that actually leads to the knowledge gap. So I recently, so our work was online on Nature Water, which actually presents a interesting observation, is we found those nanoplastics released from polyester textile during washing. Major fraction of them can be dissolved in ethanol. And later we take more analytical method to measurements to confirm that they actually in chemical essence, they are oligomers with a few repeating units. So that differentiates them from the polymeric, the polymer matrix nanoplastics, since their properties are different. And one important, so we don't know much about the oligomers, while we found there was like little evidence or little toxicity data about oligomers, but one which is very interesting paper. I would definitely recommend you to go through it. So basically in this paper, they used gut enzyme to degrade the PLA, which is a bioplastic, and they found not only micro nanoplastic was generated during this degradation process, but also oligomers. They were able to separate oligomers and tested the toxicity of oligomers, PLA oligomers. They found that oligomers are significantly more toxic and more bioavailable to mouse models, to cell mouse models. Yeah, and that actually opens up and like new areas for nanoplastic research. So do we really need to consider the oligomers, or are oligomers or the low molecular weight fraction in nanoplastics are actually held accountable for the ecotoxicity? That might explain why the polystyrene nanoplastics are more toxic than the other polymer type tested, is because like the styrene monomers, the styrene oligomers can be more toxic than the others. So with that, I would like to thank all the project partners here at McGill and in China, and also in my PhD studies who involved in all those different studies. So just before finishing my presentation, I would like to also kind of advertise our special issue. Now, still, we are calling papers from the microplastic research. So welcome. So if you have any questions, just we can also direct them to me. So with that, I would like to thank you for your attention, and the questions are very welcome.
Okay. That's a wonderful talk. Thank you. And I actually learned quite some. This is a very intensively informative talk, and which is very different from what we are doing here. I think we have some questions from the Q&A and chat. Okay. The first question. Okay, so we can also ask the audience to ask questions through audio, right? And
Yeah,
I will first read the questions from our chat and Q&As. The first question: in natural water systems, the aged microplastics may appear new and functional groups, and there is a possibility that naturally oxidized PFAS may reconnect or associated with microplastics. So will this kind of combination affect the estimated ecotoxicity impacts of microplastics?
Yeah, that's a very, very good question. So basically, I think there is a lot of ongoing research that highlights the importance of considering microplastic as a vector for different other contaminants to absorb on it and then be inhaled by or be exposed to different organisms. And I do think that kind of situation is absolutely possible. And I don't have much knowledge about this, or whether or not they are intensively studied, but I do think such study is kind of like very needed in the community. And for the aged microplastic, me myself have also done some like accelerated weathering studies, and I do find those weathered micro and nanoplastics, they really behave like very differently. For example, the nanoplastics, the weathered nanoplastics might not be like particles, or some, at least a fraction of those weathered nanoplastics might not be insoluble in water anymore. So they might become like dissolved organic carbons, while they can be classified into dissolved organic carbons as they have more like carbonyl group, which increases the solubility in water. Okay. So if you'd like to hear more about this, I can share with you the paper which is about to be accepted.
Okay. There's another question. Can you please, thank you very much for the great presentation, Dr. Yang. Can you please explain more about the mechanisms of the influence of the shape of the microplastics on its toxicity on different species?
Yeah, sure. I think for this study, well, I'm not able to show you like the detailed graph in our paper. So basically, we discussed in this paper. Well, in the 2019 paper, as well as in this as well as in the Journal of Hazardous Material paper, that the shape is actually not significantly influencing the toxicity. So it's not significant. Well, I know in some reviews they say, okay, in their database there is a significant influence of shape. For example, fibers are more toxic than the others, but I'm not sure if it is because of the shape itself. I mean, not well, natural fiber can also be more toxic than the other shape of microplastics. But for nanoplastics, it's hard. It's really hard to say since it's more in a its size is small enough to actually everything's like regular in the environment. Whereas we are testing everything like from the pristine nanoplastics in spherics, which is not very relevant, environmentally relevant, I would say. But well, it's generally spheric if you insist. I mean, even if it's irregular, it tends to aggregate into the size that's almost spherical.
Okay.
Mhm.
Thank you. Another question from the Q&A section from one of my students. Thank you very much for delivering such an informative presentation. What is the most important challenge or limitation associated with using existing ecotoxic psychological data to establish safety thresholds for pollutants like microplastics and PFAS?
Yeah, I think it's the variability. So basically the variability in different, so as we are testing the same species, we're in this case, so in this paper, we do see for definite magna, there is a like to the magnitude order of magnitude three order of magnitude of difference in even the same species. So how should we look at this data? And so my suggestion was we really have to assess its quality. So in different angles. So for example, in PFAS study, we have the 3 different dimensions with 8 specific criteria to assess the quality. In microplastics, we haven't applied, but I'm considering applying similar approach to really derive a safety threshold with reasonable data and high quality, high reliability.
Okay.
Well, another approach in the community is kind of like using statistical method or using not statistical method, but using a modeling approach to normalize everything, normalize shape, for example, normalize polymer type. But that's another ongoing discussion about the scientific roadmaps to build such a.
Okay, thank you. We have 2 more questions. Would using AOEC or PNEC might be too conservative? In some cases, in Canada, even short-term LC50s are acceptable endpoints as per CCME guideline protocol. Second, the current study is more focused on individual level. Is there any plan or demand to look into the population community level impact of microplastics or PFAS?
I think I have to clarify a little bit. So basically, all the data we use are at population level. So we're not looking at the individual's level. So the inclusion criteria is actually we only consider the study who performed the toxicity study on a population of animals, a group of animals. And second, we not only use NOAC or NOAC data, we also included EC50 data. But we have a preference. If both EC50 and NOAC were reported in the same study, we tend to use chronic NOAC. But EC50, they can be converted using 2 assessment factors, as I mentioned in the methodology part, which is the assessment factor for dose distributor and for time. We can normalize everything into chronic NOAC. And in that way, we can compare different data.
Okay, thank you. By the way, so you might be seeing that I'm not looking at your the screen, but I have 2 screens, so the questions are on a different screen. That's why I'm
Sure,
really
no problem. No problem at all.
So
yeah.
yeah, I don't know whether we have further questions from our audience.
Yeah, I
Pardon,
think
your
there's
hand is
yeah.
up. So do you have further questions?
Yes, Dr. Ju, it's actually Hassam. Can you hear me?
Oh,
Yes.
are you Jackie or a different name?
Tanya.
Oh, no,
Yeah,
no, it's okay. Yeah, Hisam, please go ahead.
thank you, Dr. Young, for this amazing presentation. So I have two questions. First off, regarding the microplastic analysis. So a lot of studies actually focused on microplastic characterization and toxicological studies, but the studies on associated additives or pollutants, other pollutants with microplastic is very limited because we have interaction with between microplastics and other pollutants such as heavy metals or antibiotics, which is a very important different mechanisms involved in these processes. So what do you think, what is the challenge regarding the toxicological analysis of the associated additives with microplastics?
Yeah, I think for me it's just very hard. Now I realize it's just very hard for people to really like comprehensively understand the toxicity of microplastics since it inevitably contains like different amount of additives in different microplastics. So I would say one polystyrene is different from the other polystyrene microplastics if the additive content in the two different microplastics are different. And since we really cannot like look at them like differently, so I would say it's hard, it's very hard to kind of like symbolize the toxicity of microplastics. You know what I mean? So as we look at the additives so if we assume the additives is the the major fraction, it induces the major fraction of toxicity.
Yep.
And then we really cannot compare one polystyrene microplastic versus another one because they're just simply different. And if we use like methods pre-treatment to release all those additives, and then we look at only the polymer matrix of the polystyrene, then it's the true toxicity of polystyrene microplastics.
Yeah.
But in other sense, it's not realistic. So there's a dilemma in it.
Yeah. So my next question is about the short chain or emerging PFAS. So majority of regulations regarding PFAS that has been established in the last few years mostly focus on regular common PFAS such as PFOS or PFOA. But regarding short chain PFAS or emerging PFAS such as ether PFAS, for example, we don't have that kind of regulation. What do you think is the reason for that, and what are the challenges and future perspectives regarding the analysis of short chain PFAS, which in a sense can be more bioaccumulative than long chain PFAS and can be harder to remove from water sources?
I actually recently came across a paper which discussed the bioaccumulation ability in short chain PFAS in an organism, and I do see the conclusion is these short chain PFAS are less able to bioaccumulate than the legacy PFAS. And as our study also shows, the short chain, which I mean C equals to 4, we don't have enough data for C equals to 5, C equals to 3, and we don't include TFA and C equals to 2. But we do see like C equals to 4 is significantly less toxic than the legacy PFAS. So in two aspects, the bioaccumulation and its original toxicity, both of them are less toxic than the legacy PFAS. So in that sense, we see like a tendency for the short chain PFAS is less toxic than the legacy ones. But again, I will see it's really complex when we talk about toxicity. So even though we see the PFOA is less toxic than PFOS, But we know that the PFOA is well documented in its carcinogenity. So PFOA is the class 1 carcinogenic substance, while PFOS is only class 2, meaning for PFOS, there is not a lot experimental data confirming its carcinogenity. So in that case, how would you say, well, PFOA or PFOS, which is more toxic?
Yeah.
So, so we really need more understanding, especially in the mechanisms. How do the PFAS, when enter into your body, enter into cell, how did they in mechanism level, cellular mechanism level, how would they attract the different toxicities?
Yep. Yeah. Thank you very much.
Yeah, and we just one more comment. We do included, as you said, the ester PFAS in our database. So, but not a lot of paperwork about it. Maybe 2 or 3.
Exactly. Thank you.
Thank you. For the audience, if you I don't know how the interface looks like in your end. If you can enable your camera, that would be appreciated, right? So
Yeah.
it's more like a face-to-face discussion.
Yeah, sure.
Just a suggestion. Thank you. This is a very good discussion, and I think we have a few more questions. One question from Tara. How do you consider the effect of nanoplastics that are not yet characterized in the models? How do you anticipate?
Well, I would say generally, as evidence has shown, well, limited evidence has shown that the nanoplastic ecotoxicity or nanoplastic toxicity in general can be due to the small molecular fraction. Then I tend to expect some nanoplastics are more toxic than the others, such as polystyrene, such as PVC. They are as the structure, the benzene structure the benzene in their structure. So I tend to think more of those nanoplastic, they are more hazardous than the others, such as polyethylene and polypropylene.
Okay.
Mm.
Okay, thank you. It seems like I think maybe it's impossible. The software doesn't allow audience to enable their camera because of this is the webinar mode of Zoom. Yeah, thank you. Actually, I didn't expect this so many questions from our audience. One question. How do you see whether this is something really safe, right, for using the current knowledge or result for the regulators to make regulations that is directly affecting potentially directly affecting the well-being of the environment and people. For example, recently a bunch of Texas farmers sued the company that sold biosolids to them, but the biosolids contains a lot of PFAS, right? And then these same group of farmers were reported to have this intent to sue the US EPA for not doing a good enough job to address PFAS or other emerging pollutants in biosolids. So how do you see this kind of now the tension between the end users of these organic fertilizers that are made from sewage sludge, right? What kind of role? How do we better promote sustainability when contaminants of emerging concerns are considered?
I think that's a very, very broad question, and I'm definitely not like eligible enough to answer that, but I do have my own perspective.
So what's your perspective that I'm interested, if you feel comfortable enough to share? Yeah.
So basically, I think generally the environmental problem or regulating environmental pollution has its latency. So so we need to wait for the effect or the adverse events will have happened, and then we then pay attention to it. Then we realize, okay, something went wrong. I think the general the general solution to this is really in the very high end, like regulating level. So we need the regulator to consider, well, before any like chemicals was applied to in our products. So do the producers provide enough information for the public or for the regulators to decide whether or not it can be included in the product? So that's a very tricky question. So that involves a lot of kind of like trade-offs between economic growth, tax paying, and saving the environment. A lot of things. So I think it's really tricky. So I do think, well, from my perspective, I encourage. So I definitely will. I'm an upholder of strict regulations. So before anything is applied or any chemicals is used, I definitely advocate for a thorough risk assessment before anything can be applied. But that's not the real world case.
Yeah. So we have to be realistic, right? But in the meantime, my perspective, my stance is similar as yours. It's like for emerging pollutants, including PFAS, microplastics, nanoplastics, that we know very little about them so far. And definitely it's a big problem. And one thing for sure is they will have some environmental and health impacts. But in order to address this problem, without knowing the complete story, it's really hard for us to solve a problem that is not understood. How do you build a reliable, really reliable regulations surrounding unknown issues? Or probably the better way for us to is really to adopt some alternatives, like to take some detour, right, to circumvent this whole thing, this whole issue, like such as biosolids. Whether there are definitely other ways of recovering resources from sewage sludge than using biosolids that we know contains higher concentrations of pollutants for land application, right? So that's my perspective. Thank you very much. And I'm curious, there's one attendee in this webinar who happened to have the same name as yours, but seems like this person is not you.
I don't know.
You don't know?
Yeah, maybe it's my wife.
Oh, okay, I see. Oh, that makes sense.
Yeah.
Okay.
I'm not sure.
Okay, great.
Maybe.
So you have a strong supporter.
Yeah, definitely.
Which is good.
Yeah, she also is involved in our project.
Oh, really? She's also in your field?
She's a biostatistician, so we do like a statistical consulting with her help.
Oh, nice. Okay, great. So you guys are doing teamwork on research. That's good.
Yeah.
Okay.
Just utilize whatever resources I have. Yeah.
Good. Thank you very much. And this is a great talk. And we are hitting the 1 hour limit. And thank you very much. Thanks to all the audience who make their time to attend. And I hope you got something from this talk. And thank you very much again to Dr. Tong Yang. And we definitely will keep in touch in future. Yeah. And I wish you all the best in your
thank you, Jinkai. Thanks to all the audience. Yeah. Of course, don't hesitate if you have like any further questions. Just email me whatever your question is.
Oh, wonderful! Thank you. This is definitely something I'm very interested, and it's a very different direction than what I'm familiar with, right? So I can definitely learn something from you.
I look forward to collaborate with you.
Absolutely, yeah. Thank you. And
thank you very much for hosting. Yeah.
Right. Thank you. I wish you all the best and take care. Enjoy the day.
Thank you. You too. Enjoy the day.
Thank you, everyone.
Goodbye.
Bye.